Part of the work I'll be showing is clustering analysis amongst all the lower mantle tomographic models that have been out there, or I think a lot of them that have been out there, to show which features amongst these models appear consistent in all the different models. And I will also compare some of them to local high-frequency waveform studies to convince you there's some value in where the cluster analysis shows the boundaries of the large low shear velocity provinces, or LLSVPs. In these models, there's also some smaller scale features that seem consistent across the different tomographic models. At the very end, I'll also show some observation of anisotropy in the D double prime. So clustering analysis is a relatively objective technique to group a data set, because you're asking the analysis to make families of your data, where within each family, the differences within the families are minimized. On the left here, when Ved and Barbara applied clustering analysis to upper mantle shear wave velocity profiles. And this is showing a clustering analysis for, I think, 7 different families. And what you see here is that features pop out like the cratons and different oceans for different oceanic crustal ages. And then you can use this to look at the average shear wave profiles at depth and see the deep signatures of these different tectonic regions. So in the lower mantle, we don't have this reference point where we know the geology, but we can do a similar technique to see what the tomographic models suggest are different tectonic regions. And this is where Ved applied it to full lower mantle profiles. And as opposed, this is clustering analysis on one model with lots of families. This is clustering analysis for just 2 families and a number of different tomographic models. So this is showing a vote map across these models. And where it's bright red here, all the models agree on it being a slow profile here, and where it's bright blue, all the models agree on it being fast. And you can see on a lot of the boundaries, there's quite some agreement. This is then, so we set the difference between the profiles as the L2 norm. This is the mean profiles in these different models that come out of this clustering analysis, where you see the clear slow signature and the fast signature. So these are the 2 different families. In this case, the clustering analysis is really dominated by the signature in the lowermost mantle. If you were to cut off the lowermost mantle, you get a very different vote map of where these 2 families would lie. So Ved and I extended this to using a sliding window of the profiles in the lower mantle to see more what the 3D suggestive morphology is of these LLSVPs. And we find that we do that we cannot cluster the lower mantle in 2 families. As well, in the lowermost mantle, we see this dichotomy between slow and fast anomalies with a strong gradient in between. When you go to the mid-lower mantle, we see both fast anomalies and slow anomalies that are both suggested to be surrounded by strong gradients. You can see this for a slow anomaly here, and for example, for a fast anomaly over here that's surrounded by strong gradients, but the gradients don't necessarily go from fast to slow anomalies. And so there's some need for a third family, which kind of represents a neutral or a background lower mantle. And so so we extended with the sliding window. We extended by using three clusters, and then we applied it to a range of the shear wave velocity tomographic models that are out there. To simplify the color map, I'm only showing the results for 5 recent models, excluding Paulo Coulemin's model because it's up to degree 12. And so because we now have results for different depths, I will show these depth slices. But first I'll explain this color scale of our vote map. So the edges of this color scale show where all the models agree. So bright red, bright yellow, and bright blue is where models agree on all models voting slow, or all models voting neutral, all models voting fast. And then in this outer triangle, there's the trade-off between slow and between neutral and fast. So an orangish color here would mean that 3 of the models are voting slow and 2 of the models are voting neutral. And the greenish color means that 3 of the models are voting fast and 2 of the models are voting neutral. Then in the center here, we've made the colors murkier. And this is where models don't agree have disagreement on being slow or fast. So in this inner triangle, 2 models would be voting slow and 2 models would be voting fast. But overall in the lower mantle, 95% of the region is represented in this outer triangle in the bright colors. And this inner triangle is only 0.1% of the volume. So you mostly see bright colors in our maps. And we generally jump to interpreting the fast cluster as slab material, so compositionally different material coming into the lower mantle. The slow cluster is more difficult to interpret if this is a purely thermal or thermochemical variation. If there was a chemical variation with a thermal anomaly on top, we wouldn't necessarily distinguish that with this method. We kind of put a prior assumption in this method that there are sharp boundaries somewhere, and then ask where the tomographic models would put those sharp boundaries. But we don't really give an answer to this question or how sharp the velocity jump is at those boundaries. But I think Andy Nowaski will say more about this in his next talk about how these different models could create sharp boundaries in the lower mantle. So here are different slices, different clustering analysis in these windows. So this is running from 1,100 kilometers to the lowermost slice that we have. We kind of stop at 1,000 kilometers because everything breaks down above 1,000 kilometers. You see the fast cluster has general agreement on the giving long linear features that go down, and then a large accumulation in the lowermost mantle, while the slow cluster tapers out as you go into the lower mantle, and really is only high in 3 regions beneath the superswell in Western Africa and beneath Eastern Africa. And we repeated this exercise for 5 P-wave tomographic models. So here is comparing the S-wave map to the P-wave map. And we generally see a lot more disagreement in the P-wave models. So there's a lot of these murkier colors, especially under the Central Pacific, where the coverage in the P-wave seems to be less. But a bit later, I'll show you some small-scale features that actually appear clearer in the P-wave models than they do in the S-wave models. So here are some cross-sections through the LLSVPs. The vote map suggests a wide variety of the shape of the boundaries of the LLSVPs. So if you look along the length of the African LSVP, which is this cross-section C here, you see both very shallow sloping boundaries in the south here, and then on the western side, very, very steep vertical boundaries. And if you look at the cross-section D, you see a suggested overhang of the African LLSVP. And so this suggests a wide variety in the dynamics of these features, either due to compositional variations internally or due to interactions with the surrounding dynamics. Just to emphasize, because these vote maps kind of give the impression that these are uniform features in some way. So here I'm plotting the boundaries where 4 out of 5 models agree, just shown here. So in red for the slow, and yellow for neutral, and blue for fast here. And I'm graying out all of these areas in between here. And I'm showing you the main velocities in the background in these clusters. And so you can see that each cluster in the map here and in these 2 cross sections, each cluster represents a range of seismic velocities. So they're not necessarily internally uniform, and part of that non-uniformity could cause these differences in the shapes of the LLSVPs. I'm now going to compare these to some local waveform studies and what has been suggested by this. So this cross-section across the African LSVP, where we see this suggested overhang, has been studied a lot in waveform studies. And some of these studies have suggested this overhanging feature in the green outline here. And other more recent studies have actually shown that this model cannot exist and it needs to be more of a bell shape. Obviously, this clustering analysis of the tomographic model seems to agree more with this type of model of a very high anomaly with an overhang. In the Pacific, the high-frequency waveform studies have found more separated piles, and that is what also comes out of the clustering analysis. So this is work by Hay and One that see a separate Western Pacific anomaly that's very high and has very steep sides, and then a Northern Pacific anomaly, which has a much more shallow sloping sides and is much smaller, and some separation between the two, which we don't totally see. I've tried to reproduce where this cross-section is in their study, which this might not exactly represent, but we see the same general trend of a higher, steeper, and a shallow sloping lower anomaly, although our suggested heights are a lot higher. We do have some smearing in height because we do use these 300-kilometer windows to do the clustering analysis, but we do see the LSVPs being much higher. This is work by Frost and Ross, which look at P-wave travel times at high frequencies. And so here they're looking across the eastern boundary of the Pacific LSVP and the northern boundary of the Pacific LSVP. I've mirrored the image here. And they see a very difference in slope between these two boundaries, ranging from 70 degrees to around 25 degrees here. And I've copied their slopes onto the cross sections in our vote maps here. And so we see good agreement on very, very steep slope at the eastern boundary of the Pacific LSVP, and a very shallow slope at the northern boundary. And we can see this extends a lot higher, a lot further than their data coverage can tell us. And they suggest that this difference might be due to slab material being present here that might be pushing into the pile, as opposed to no slab material being present there. We kind of tried to look for this relationship in all of our clustering analysis boundary to see if that was a general rule, but we don't see a consistent relationship between there being slab or suggested slab material in these fast anomalies right next to steep boundaries. So this is then a contour map of where, in red, where all the models agree, and in yellow, where the majority of the models agree. So overall, if we were to make estimates out of the volume in this, we do get a lot higher estimates. In individual models, it ranges from around 8 to 9% slow velocities, but if we look at the consensus between all models, we get a 4% estimate for the LSVP, which is a lot higher than has been suggested by previous studies of waveform modeling and of taking contour maps in tomographic models. And we also see that the African LSVP is suggested across the models to be 30% larger than the Pacific LSVP. So there are some smaller scale features that come out in these models and then appear to be consistent. So while in an individual tomographic model you might not interpret every small blob, here we see some that appear more or less consistent across the different tomographic models. And this one is probably the most consistent. We studied this after the 2012 clustering, that there was this smaller anomaly of slow velocities beneath Perm. And this is an event from Spain to stations in Japan and Taiwan. And in these waveforms, generally travel through fast anomalies here, and then we see delayed waveforms here where they travel through the Perm anomaly. And so here we modeled this with a very simplified cylindrical slow anomaly to fit these travel time delays. This is showing the Perm anomaly in our clustering analysis that is now 3D, and the dashed line is our simplified cylindrical anomaly. And you see it generally agrees. We did not have good resolution on the height in our modeling, and this is the southern boundary of the Perm anomaly, which we also didn't have good data on because we don't have any coverage there. But generally the shape agrees. And the modeling here suggested that the velocity reduction is quite similar to the other LSVPs, so it's suggested to be the same material. See the suggestion of another such feature here in the South Pacific that appears to be separated from the rest of the Pacific LSVP. A separate anomaly. It's slightly larger than the Perm anomaly. Is suggested to be in the clustering analysis. And I soon tried to look for waveforms that give evidence. This work is very preliminary and non-conclusive at this point. This is plotting the travel time differences between S-diffracted waves and SKS waves. And while we do see that we get lower travel time anomalies over here, maybe suggesting that this is a corridor of faster velocities here, we don't see any very clear evidence for the South Pacific anomaly. But unlike the Perm anomaly, this is a much more complicated regions because all the waves travel through LLSVP material on their source side, and so we need to correct for that in some way. We're also trying to do some tests with this to estimate how well our estimates of the LSVP boundaries work by looking at what the mean velocities are suggested to be. So this is showing the correlation between path length and the LSVP, or the differential path length between S diffractant and SKS. So the ones with negative path length here mean that the SKS has been traveling more in LSVP than the S diffracted, versus the differential travel time. And so you see we get somewhat of a correlation, but there's still a lot of scatter in our data. And this scatter results in quite a broad range of estimated mean LSVP velocities, which do peak at -2.5%. But we still have to look how geographically where these missed or potential missed estimates are, and potentially we're misestimating the LSVP boundaries there, or can get more information out of that. Here is another more mystical feature which sits beneath the Kamchatka. And what we're actually seeing here is that this anomaly does not come out very clearly in the S-wave photomap map, but then comes out quite consistently in the P-wave photomap map. And I cannot say at this point if this is a matter of a difference in resolution between these two types of models. I wouldn't think this is a location where there's necessarily a lack of S-waves. The other option is that this might be actually representing material properties in this small-scale anomaly. Suggestions of this anomaly have also been seen in the travel time study by Frost and Rost, where they were looking at the eastern boundary and the northern boundary of the Pacific LSVP. But they also see suggestion of a sharp boundary up here in the northern Pacific. The background model here is gypsum, so you can see there's also slow velocities in that model. So this is a P-wave velocity model, and it's one of the models that provides a slow map, a slow vote in our vote map over here. There have also been suggestions of complexities in shear waves. So this is a study by Hay et al. That look under this Kamchatka region, although their sensitivity seems to be slightly west of where we see this anomaly. But they do argue that there's a slow velocity in shear waves that extends over great high, but reduces rapidly in its amplitude, but is surrounded by high velocity zones, which might explain why it's hard to see these features in shear waves. And just for fun, I plotted here the difference in the votes for the slow anomaly between the shear wave models and the P-wave models. And so greenish colors here mean that a lot more of the shear wave models vote slow, and brownish colors means that a lot more of the P-wave models vote slow. You see that a lot of the disagreement lies around the boundaries of the LLSVPs. For example, the P-wave models seem to have less agreement on the South Pacific anomaly being separated from the rest of the LLSVP. There seem to be spots where the shear wave models vote a lot more slow. These seem to be at boundaries where ultra-low velocity zones have been measured. So I don't know if these are kind of leaking into the tomographic models. But aside from the boundaries of the LSVPs and the boundary of the Perm anomaly, the only big anomaly seems to be this Kamchatka anomaly that comes out consistently in the P-wave models versus the S-wave models. Then this is getting more and more speculative, but there are some regions where we kind of see floating anomalies. This is a cross-section beneath the Amazon, and beneath Indonesia over here, and beneath Arabia over here. And this is what the S-wave model suggests. But then in the P-wave models, we see more consistent blobs here that appear in several of the models. And obviously, I can't say anything about the dynamics of these, although I think they have some constraint on the dynamics that are happening in the Lowermost Mantle. And they make me think of the blobs that Anne Devay showed yesterday, of potentially plume reaching neutral buoyancy somewhere, pieces breaking off and sinking back down somewhere else. So I'm slightly going to switch gears now and show some observation of anisotropy and its relationship to the LSVP boundary. To do this, I'm using S-diffracted waves at very large distances. So when the S-diffracted wave propagates along the core mantle boundary, the SV component attenuates very quickly. It loses energy to the core. And at these very large distances, above 120 degrees, you expect the S-diffracted wave to be polarized along the SH component. So different from the SKS waves that are polarized, coming out as V polarized from the core, these also have a single polarization, but in the SH direction. I'm looking at an event from the southern Fiji region and coming up to the Campbell array in Africa. And this is where they enter the lowermost mantle. This is where they diffract along the core mantle boundary, and then they come up through the lowermost mantle over here. And what we see in these observations is in the SH, you see a strong delay in time. So this is the waveforms here are organized south to north. And so the northern waveforms here travel through the LSVP and are delayed over here. On the SV component, we would not expect any energy. But what we're seeing here is strong energies both in the southernmost waveforms and in the northernmost waveforms. And if we look at the particle motion, so here I'm plotting both the horizontal components and as a function of time. So time is running here from blue to red. And what we can see here is that in the southernmost stations, the waveforms have an elliptical particle motion, meaning there's a time offset between the SH and the SV component. And this is a signature of anisotropy, so they've traveled at two different speeds. And in the north, where we also see some energy arriving here, it's a linear particle motion, and this means that the SH diffracted wave there is arriving from out of plane, potentially due to refraction at the LSVP boundary. So this is not a truly separate energy, while here we see two different waves arriving with a travel time anomaly. And we can measure for the southernmost station the splitting that is occurring in these waveforms. And as a function of azimuth, this seems to decrease towards the LSVP boundary. So a separate argument to put this anisotropy into the lowermost mantle is to compare with the splitting of the SKS and SKKS. Definitely, SKKS wave seems to have a very similar travel path in the upper mantle. And so if the anisotropy was in the upper mantle, it should see a comparable signature. You see here in the particle motions of the SKS and SKKS, they're a lot smaller and there's a lot more noise in here, but we do not see a similar trend in this increase in anisotropy as we see in the S-diffracted waves. So we put the anisotropy can only occur here in the lowermost mantle, where the S-diffractive waves go up to the station. It cannot be on the source side either, because any SV energy would have dissipated while it was propagating along the core mantle boundary. These are comparison with synthetics. So these are prem synthetics, where you see the mostly SH energy arriving. This is with an isotropic model, where we're capturing some perfectly all of the multipathing that might be happening around the LSVP boundary. And then we implemented an anisotropic model. So we can really only say very little about the elastic tensor here. We only have one observation along the path direction of this fast axis. And so we map this fast axis as in this elastic tensor as a kind of azimuthal anisotropy, and then rotate the azimuthal anisotropy in the direction of the wave propagation that we have here. So pretty much this is the only bit of the elastic tensor that we actually constrain with one such observation. And the strength of the anisotropy is very unconstrained depending on how thick I make the layer of anisotropy. But here I put 8% anisotropy in a layer of 150 kilometers to create synthetics that kind of match these splitting parameters over here. We don't totally match the amplitudes of these waves over here, but we match the general splitting component between our synthetics and the observations. And so this lies in a general group of observations that have been made with SKS and SKKS differential splitting, which seems to always show stronger splitting outside of the boundaries of these LSVPs. You get discrepant splitting across these boundaries, shown across the African LSVP here, and around the Perm anomaly over here. And so there seems to be a general trend of strong anisotropy, which here in the cartoonish view I showed in terms of flow, outside of the LSVPs, and then some sort of mechanical boundary and no anisotropy within the LSVPs. So in conclusion, I've shown that we can characterize the lower mantle into 3 different families, and that these have a suggestive very varied morphology of these LSVPs, which seems to be often consistent with these localized regional waveform studies that have been done at higher frequencies. And we also see some suggestions of smaller scale anomalies that definitely need more work in terms of waveform modeling to confirm if they're there and what kind of material properties they have. And then at the last little bit, I showed an observation of anisotropy outside of the LSVPs. Thank you.